Okay, first of all, what is the Leibniz association? It's very similar to Max Planck. You know that, same but different. It's one of the 4 German science organizations, and the main difference is that we have a different funding and that we are a little bit more application oriented, maybe. And we are good friends and neighbors even with Bernd Schneider, who came from our originally from our institute actually. So we meet from time to time. So what do we do in our institute? We look at plants, as the name says, on the molecular level and mushrooms and associated organisms. We try to extract all the molecular information biologically and chemically, and develop the tools to analyze these data, of course. And that is one of the major differences to some other institutes. We try to reapply that in terms of, let's say, breeding, agrochemical applications, but also for applications, whatever we get out there for human use, going into things like health, nutrition, and so on. And I don't want to give you the political blah blah of the great challenges and so on. You know how this works. So why plants, or why plants and fungi? There is, of course, this what Aristotle has said, great Greek at those times, not a liar. So it was not about finances. But Aristotle, as scientists, you should ask yourself, okay, is this true? What does better mean? Better is not defined, you know. We always hear natural products are better. Are they really better? I mean, not really, but they are better in one aspect, and that is the propensity or the chance of finding active compounds. It's not that the compound itself is better, more healthy or so. A natural product is not more healthy than a synthetic one. That's nonsense. But the propensity, the chance of finding something is much higher. It depends, of course, on what you look. And we are, for instance, especially interested in anti-cancer area. And if you look in the anti-cancer area, there natural products make less than 1% of the tested compounds, but about 2/3 of the drugs or the inspiration for drugs in that area. For anti-cancer drugs, it's mainly from plants. For antibiotics, it's the same numbers, but it's mainly from fungi and other bacteria. So you have a higher chance of finding active compounds from these organisms. And these are all, of course, and what I'm talking about today is untargeted metabolomics of secondary metabolites, and there is a few 100,000 out there. So it's quite a big difference to what we hear when we hear metabolomics from human origin and stuff like that. So most of what we talk about is absolutely unknown, and you don't have one method to extract it. Every plant is different. There is not one single method. You have to adapt it to every problem you have. But the big advantage is that all what these plants provide, so they are selected by evolution for activity, and that's what makes them interesting. Now when we look at this and we look at these plant constituents, MS has a very high resolution. We need very little compound. So this is a picture of MS. You see it, but you don't get all the things to fly, especially not in a complex matrix. NMR shows you everything, but the resolution is very low. So the first thing what we did is, when we looked into plant metabolomics, is to compare the two methods and what they bring us, and where one or the other is more useful. And that is something which is, I would advise everybody who goes into this to really look at both methods. And very often we see that both methods work if you have the right way of sampling the data, and if you know which areas, for instance, in the NMR to keep out. For instance, sugar area, you should skip that, and then you get very similar examples from MS, although you look at other compounds, interestingly, but the PCA is often then very similar. This is just an example. You can see this comparison, MS, NMR, in these two papers. One is based on hops. This is hops cultivars, you know, for the beer drinkers, very important. And the hops cultivars are very different, and you can sort them according to year, according to genetic origin, and so on, by these methods. So very recently we've done some new methods to analyze 2D NMR by having a pixel analysis evaluation tool designed. where we can, this is HMBC, so hydrogen and carbon spectrum, in that we make pixels are what you could call it binning, but why invent a new name for something which already exists? So pixel exists. I mean, that's one of the problems of metabolomics, that lots of stuff which have been invented before are reinvented with a new name. So you want to take the new name, you want to be the emperor with the new clothes, but you maybe end up naked at the end. So it's better to stick to what is. So we don't call it bins, we call it pixels, because they are pixels, and this is the name it is. But these pixels, you can put them in a row, and then we looked into how big these pixels should be to give you a discrimination and so on. And then from these pixel analysis, which you have linearized, you can then run the comparisons. We have done that for a number of food and medicinal plants with different standards, difficulties. For instance, in hops, it's just the same species, but many cultivars, commercially important. With urtica, we had more than 53 different species. So we are not keeping within one species, which has its dangers, of course, but in urtica was not so problematic. It's not so rich in metabolites, by the way. It's only a few hundred per plant. Whereas Hypericum or licorice is extremely rich. Now, we not only compare the methods which we use, we also use other methods. We also compare the different analysis and statistical techniques for the purpose which we have to, and this is important to know which one is fitting which problem. So here you see metabolite profiles of Suillus species. Suillus is a sort of a mushroom which has very special aromatic prenolated compounds which have some activity I come to later. Anyway, when you look at it, some species are very similar, have the same compounds all over, and there is a few differences, but not so many. And we can find out about these and distinguish all the species on a species, but also on the base of how you call it, of cultivars. Okay, I skip this. I also skip this. You can, what we want to do at the end is, and that is, now we're coming to the important message. What most people do is PCA and other stuff, but that is all not useful if at the end you want to find out which compound is responsible for what biological purpose. Because then statistical general input is not good enough. You want to know what specifically one compound does, and for that you need other biological tools than general statistical tools which give you some parameters at the end. So you want just the opposite of a principal component, which is a mixture of some components which contribute to something. You want the one which, or the two or three which are responsible for biological activity. Now, in order to do that, you can have tools, you need to develop tools so to get that out. So conventionally what you do is you take, make an extract. First you start with some data mining, to find out which species contains which compounds which are connected to do something for the disease you're targeting. And if you want to do that, for instance, you can use the tools, this ontological tools. OC Minder of this is one of the companies which we formed based on our technology some years ago, which is in market since 10 years now. But still, this gives you only hints. So how do I get really to the stuff I want? Well, the first thing is, it's very dangerous if you think that something which you have found or which is interesting from literature can be found again. That's not true. Because very often you have plants, you have collected them, you get the same species 2 years later, and it doesn't contain the same stuff. Or with microorganisms, just here an example. This is our culture collection. We have a big culture collection of more than 5,000, 6,000 fungal strains in our institute. And we found some interesting stuff in the Cepedonium ampulosporum. Now if you compare the metabolites, metabolomics in NMR, they all look the same. There is minor differences here, and these are the ones which are important. Now if we do a PCA on those, then we find out that when we have this Ampulosporum strain, which contains the interesting stuff, the other Ampulosporum does contain totally different compounds, because what we see here is of course a representation in the differences in NMR, and NMR again corresponds with the corresponding chemical groups which are present in that organisms, and we see that a different species is much closer chemically than the same species in a different strain. Okay, so that's an important message. So we thought, okay, then how can we use this to discover the few active compounds which are cannot be seen in this standard PCA analysis, and so we see these few active compounds in a huge unfriendly matrix, where in reality mostly the needle is hair yellow and not ferromagnetic, if you think about that. Now that's the standard, which we have to cope with. And the standard chemist done it so far. Many will know, you start from the organism, from the sample extraction, you fractionate the whole stuff until you end up with your 50 compounds which you can isolate from these 1,500 which are in that organism, and you hope that within these 50 compounds is the one with your activity. The other way to do the whole stuff is you do an extraction, you process your sample, just for instance the crude extract mostly does not work in plants because have you ever wondered why in these why you have these plants where they claim 1,000 activities, anti-HIV, anti-cancer, anti-something, anti-this? You know what that is? That's the polyphenolics which just react with some proteins. They just it's the tanning of the proteins, and then of course these proteins don't show any activity more. Of course then your assay shows you that the enzyme doesn't work anymore, that the bacteria are clogged together, because you're just tanning the whole stuff. That's why you use oak tree bark for tanning. That's nothing than gluing the proteins together, and then of course you get no response anymore from your assay. So it's not a selective action. That's what you don't want. So you need sample processing. You do the bioactivity, and then you take those fractions which have the best bioactivity to the next separation step. And you go in this bio-guided isolation, you go this separation, testing, taking the best extracts, you take that in the rounds. Now imagine you have an assay, and we have done that. Learning assay for Drosophila, so to find compounds which learn. One assay takes you about 30 days, and you can about 2-3 assay spots per month. Impossible to do this. It would take you years to go through this circle of bio-guided isolation. But anyway, very often it works if you have a fast assay, and then you can get to you can isolate the compound which is responsible, but very often you end up in nirvana with this approach either. Because you have the activity in the whole extract, but you have no activity in your separated extract. It could be additive effect, it could be that all this processing is destroying your compound, it could be that you have synergistic effects which you separate during the separation processes, and so on. So this is the disadvantages of all these major two techniques used so far. So we thought, okay, is this the end? Of course not, because we have two things. We have metabolic profiles which show us in principle, without knowing which every compound, it also must show the needle, logically, if it really omics, I mean. And also, we know the biological property because we have measured them. That was what made us interested in this extract at the beginning in any case. So we need to connect these two things. We have all the information in two bunches of information which are so rich that we don't know how to bring them together. But can we do that? And we thought, okay, we reverse the process. What you do in normal metabolomics. In normal metabolomics you have two different, one treated and one untreated sample, you compare them. Now we take different samples and see where they are different, and if that compares to the activity. So instead of isolation and then characterization of the compound which is responsible, We do first the characterization of the extract and then the isolation, and that saves us from doing all the dereplication. That means to replicate all the compounds which are relevant, which are in there, because usually you find, I mean, the first 50 compounds you find in any plant are almost the same in all the plants or mushrooms, and they are not the interesting ones usually. So how would that work? In principle, one of these compounds represented by one of the peaks or one of the MS or one of the NMR signals is responsible for your activity. And so, in quantitative terms, a higher content of that should give you a higher activity. A lower content should give you a lower activity. Whereas other compounds wouldn't show this type of activity correlation quantitatively. Oh, we have a hard time to eat the 3 minutes. I talk myself too much. So what we do is we run the bioactivity profiles, we run the metabolic, or I would call them rather metabolomic fingerprints, and then we have an activity correlation analysis, which is software we wrote, where you get a hit list. So what correlates best, what correlates second best, and so on. With that, you know the ones which correlate best, you know already their exact mass, their elemental composition, your fragmentation pattern, and the retention time. So you know which peak to isolate out of these, which are the most interesting ones. And once you have isolated them, you can put that to the individual test and make out of the correlation a causal relationship, because the correlation is just a correlation, you know. So you have false positives. So this is the whole workflow. You have your extract, you do a bioassay, you do the metabolomic fingerprints, you can do standard data analysis. That doesn't hurt you here, it can help you, but then you do your activity correlation analysis with a positive correlation. You can also have negative correlations. You isolate those which are necessary, do the structural elucidation, and then we go to the target finding, proteomics, activity-based protein profiling, and so on. So what are we interested in? Anti-cancer compounds mostly. Do also some hormone receptor stuff, antibiotic assays with a special emphasis on antifungals, but we also work with antihelminthics and so on. And of course in a plant institute we have some plant abiotic stress assays. How does it really work? Well, to check that, we did some years ago a proof of concept in which we took extracts which have no or low antibiotic activity themselves but are very complex, and we spiked them with 3 antibiotics, one bactericidal, bacteriostatic, and one which is close to inactive to our test organism. And we spiked that in various concentrations. And what we got out with our method is a suggestion of about 3% of the peaks which were significantly correlating. That means that you have only to test and isolate less than 3% of what is in there. Imagine, you save 97% of the work, yeah, which you have to do normally. And in this we found the rifampicin and the erythromycin, and not the amoxicillin because it's not active. And we find even impurities in these antibiotics, which were also antibiotically active. We didn't know that such impure stuff is sold to us, and we take it. And we have other identified compounds which are either false positives, just coincidental correlation, or which may have some underlying antibiotic properties which we didn't look into detail in. So getting into the real world, we could use that to find out compounds of interest in acetylcholine esterase inhibition. We found bactericidal compounds, cannot give you details here. One of our hits was a very simple fatty acid compound which we patented, which is now in worldwide field trials with BSF as a fungicide. We find that was from mushrooms. We found a number of stuff from plants. But then we thought, and now coming to the last 2 minutes, we thought, can we get more complex? Can we do something really risky? Now we always compared complex mixtures with a single property. But what if we have a very complex property like taste? For instance, meat taste. You have all these properties here, and some of them, you know, are very important for getting a good feeling of meat. That things like juicy or so. But how does juicy translate to compounds? Yeah, salty you can imagine, but can we measure salty? Obviously not, because we are only in the organic compounds. But we still said, let's try it. And we had a company partner, Symrise, one of the big companies in flavor and food markets, and they gave us their from the taste panels the data, and we got also the spectra from them, or some we did ourselves where they didn't have them, and we correlated these spectra to the taste, to the likeness of the taste. And then we got a hit list, and we got some compounds out which are responsible for that taste. And we found even new compounds which they didn't have on their list yet for being important for the good steak taste. I mean, that's important for Texas, isn't it? And in the NMR, it showed that some of the important compounds are minor compounds. And we did MS. I don't show you the MS here. We did MS too, so you get to the compounds which are even lower, like the sulfur compounds. You would never see in the NMR because they are very important, but they are they act in a PPT area or PPB area. They are very low abundance, but still have a very important influence. So then we took the 14 most important compounds from our list and made an artificial aroma block mix and added that to a bouillon base, and indeed it tasted much meatier than the standard. So it was more juicy, it was more salivating. The acidity is because it was adjusted to a pH 6. That's just for the normalization is important. So you see that in almost all parameters it had higher impact on the taste than the standard. And also you can test the single compounds versus the block, and those customers who rank that highest are always rank this combination highest, and it was the best combination for a meat taste ever done. Now, I can tell you this and show you the samples because you'll never get to the market because the compounds involved to get this fine, nice taste are much too expensive to really bring to the market in your bouillon. But still, it was very nice for us to see that we can really compare not only a matrix of hundreds of compounds with just one property, but also with a mixture of subjective properties, and still get reasonable results out. And that for us was very amazing, and for the company too. And yeah, this is the conclusion of my talk. I would like to thank the group, the cooperation partners, and of course the sponsors. I don't name them all. You can find them in the papers. I just want to take out Mohamed Farag, is an Egyptian postdoc, now professor at Cairo University, who did most of the metabolomics on the medicinal plants, because he's an exceptional scientist, was in this area the most cited scientist of Africa last year, and he was postdoc with my group, and I think he has a great career. So if you see anyway the main name Mohamed Farag, remember him. He's a great guy. Thank you very much.